welcome back. This is 4.1a. If we drive 50 miles per hour for 3 hours, we travel 50 times 3, which is 150 miles. Recall, distance equals rate times time. So in our case, the rate is 50 miles per hour times 3 hours is going to give us 150 miles. Okay, let's say we drew a picture of this. All right, where we make the horizontal axis t in hours. Put hours right here. And we make our vertical axis the velocity, in this case miles per hour. So I'm going to call this v for velocity. Okay, we're going to split this up into hours. 1, 2, 3 hours. And then we put our velocity at 50 hours. I'm sorry, 50 miles per hour. Okay. All right, so we're going 50 miles per hour for 3 hours. All right. Down here. Let's look and see what the area under the curve represents. If we take this area and we have 3 hours times 50 miles per hour, we have 150 miles. So we can see the area right here equals distance. Okay, and area equals rate times time, which is the distance. All right, so let's do another example. We have a truck driver and the truck driver, he starts on a trip and he speeds up. He speeds up linearly from 0 to 60 miles per hour. All right. And that happens in the first 15 minutes. Truck driver speeds up from 0 to 60 miles per hour in the first 15 minutes. Okay. Then he drives for 1.5 hours. All right. After he does that, he slows down, back again linearly, and he goes from, you guessed it, 60 back to 0. 60 miles per hour back to 0. So the question is, how far did he travel? I should say he or she. How far did he or she travel? Okay, so let's draw a picture of what this would look like as well. We're going to put it on a plane. We're going to split it up. Okay, so here we go. This is going to be our t in hours. This is going to be our velocity. And he goes, the highest he goes is 60 miles per hour. Okay, so we're going to go 2 hours. All right. Now, he goes from 0 to 60 in the first 15 minutes. We know 15 minutes is a quarter of an hour, 0.25 of an hour. So these are in hours, so right here, 0.25. 0.25. So he's going to go zoom up to 60 in the first 15 minutes. Okay? And then he cruises at 60 for how long? It says an hour and a half. Well, if we start at 0.25, this is 0.75. And this would have to be 0.75 to here. Here we go, 0.75. That makes an hour and a half from here to here. So he's going to cruise 60 all the way to here. And then he goes right back down for the last 15 minutes. 0.75 to 2, 0.25 in there is the last 15 minutes. And we go straight down. Okay, so we want to know, how far did he drive? Well, we know area is distance. Well, what we could do is we could break this up. I know my shape's a little off. Imagine that's 0.25 right there. And then we split this down. So we could find the area of this triangle, which would be the same as the area of this triangle, and the area of this rectangle, and that would give us the distance. Okay, so we know the area of a triangle is 1/2 base times height. All right, in this case, 1/2 the base is 0.25, and the height is 60. All right, and that equals 7.5 miles. Now let's do this space in here. We said this was 1.5, and that's 60. Okay, so the area of this rectangle or square, whatever it is in reality, is going to be 1.5 times 60, which is 90 miles. Okay, so the area of this trapezoid is going to be, we have two of these, 2 times 7.5 plus 90, which equals a total of 105 miles. Okay, now let's say we wanted to find the distance of something more realistic of how we would to drive. Okay, let's say we started driving and then we go faster and then we go slower and then faster, slower, and then we stop to where we are. All right, so how can we find the area under this shape right here to find the distance? Okay, and I'm going to show you how to do that later. All right, we got to start off with something called left rectangle approximation, with something a bit easier, and we'll work our way up to doing a problem like that. Okay. All right, so draw something like this with me. We're going to start here and go up. This will be 1. This will be 0. And then we're going to go out 2. 1, 2. Okay. We have something called left rectangle approximation. Left rectangle approximation. And we will use a capital L to signify that we're using left rectangle approximation. And here we can say the area is approximately L, and we're going to split this up right here into 4 equal parts. So this is 0.5, this is 1.5. So we have 1, 2, 3, 4 equal parts. And then what we do with those parts is we make actual rectangles. So here's one rectangle to find the area. Now this is 0.5, so this point is f of 0.5. And then we go straight across and find the area of that one. This is 1, and this point is f of 1. And from here we'd go straight across and down. Okay, this is 1.5, so this point would be f of 1.5. And we go straight across and down. Now you can see that we're missing some pieces right here, but it looks pretty good as getting the area under there. So if we were to write this out, we split it up into 4 equal parts, and the distance from here to here of each equal part is 0.5. Okay, so we'd say 0.5 times 1, this times this, is the area of that little piece. And then we go on to do this piece, right here, which is 0.5 times f of 0.5. 0.5 times f of 0.5. Okay? Then we do 0.5 again times f of 1 plus 0.5 times f of 1. And then our last piece, 0.5 times f of 1.5. Write this down here. F of 1.5. Okay? Well, let's do a real example. We're going to let f of x equal x squared plus 1. And we're going to approximate the area. Approximate the area. So area is approximately, and we're going to split it into 4. All right? So we have 0.5 times 1. That's easy one, right? All right, then we continue. Plus 0.5. Now, how did I get 1? Yes, it looks like 1, but why? You're probably wondering why. If you put a 0 in here, 0 squared plus 1 is 1. So that's how we did that. Okay, the next one, 0.5 times f of 0.5. F of 0.5 right there. So we have to put a 0.5 in there. We have 0.5 squared plus 1. All right? Plus 0.5 times f of 1. F of 1, we put a 1 in there. 1 squared plus 1. Plus 0.5 times f of 1.5. So we wouldn't need this f right here. We're going to actually put 1.5 in there. 1.5 squared plus 1. All right, so let's simplify. 0.5 plus 0.5 times 1.25 plus 0.5 times 2 plus 0.5 times 3.25. Okay, now a much easier way to add them all up, instead of multiplying all these and adding them, notice they each have a 0.5. So let's pull out that 0.5 and write what's left inside there. Okay, so we factored out the 0.5 and we add them all together and our end result is 3.75 units squared, whatever that is. Okay, now we may ask ourselves, how can we do this where we get a better area, where we're not missing such big chunks right there? Well, what if we split it up into 8 separate groups? Okay, so let's draw a little picture. And we're going from 1 to 2, and we split it up into 8. So that means we have 0.5 here, 0.25, 0.75. Let's see, let me split this up. Okay, so we have 8 equal parts. So in this case, the area is approximately to L8. Oh, look, it's my cat just walked up. Okay. All right, so notice here, this 0.5 right here is our delta x. Our delta x was 0.5, 0.5, 0.5, 0.5. So down here, our delta x is going to be 0.25 because we're splitting it up into 8 equal parts of each 0.25. Okay, so this would look like delta x times f of 0 plus f of 0.25 plus f of 0.5 plus dot, 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 dot. We're not going to write those all out. F of 1.75. Okay? So what this would look like is delta x is 0.25 times all of this inside, which ends up being, if you want to do it on your own, 16.75. And the answer is 4.1875. Now notice, this number is more accurate. It's larger than what we got when we split it up into 4 parts. So splitting up into 8 gave us a more accurate area. Now, what if we said, well, we want to know exactly what that area would look like. We have a way of doing that. Okay? And we're going to get there, but I'm going to show you how we're going to start to get there. We have this formula. It's called the definite integral. Definite integral. Area equals, we're going to integrate from point A to point B of f of x dx. Now, what does this look like? Okay, let's draw a similar picture that we had. This would be point A, this would be point B, and we're going to integrate from A to B, and this is f of x, of course. And by integrating, we would find the area under that curve. Okay, so in our little example, we want to know to integrate from 0 to 2. Okay, we want to find out what this area is under the curve. All right, so we would say the area equals, we're going to integrate from 0 to 2 of x squared plus 1, because that's what our f of x was. Now, we're going to learn how to do this later. I just want you to know there is an exact answer, and the answer is 4 2/3.